Hello TNA, and welcome back to lesson 4, which is all about gravitational potential energy. Now we're going to look at comparing the relationship between kinetic energy and gravitational potential energy. Remember that kinetic energy is the energy found in moving things, and gravitational potential energy in things that have height. Well, in order for something to get to a height, we need to move it there. And for it to come down from that height, to lose gravitational potential energy, again, it needs to move. So that's how those two are very closely linked. And we're going to look more and do some calculations about that. The law of conservation of energy, pause there, write down your definition of the law of conservation of energy from a couple lessons ago. All right, welcome back. Hopefully you have written down that the law of conservation of energy is the fact that energy can't be created or destroyed only transferred. So all the energy in the universe, it can't be created or destroyed, it can only be transferred. All right, and it's through the 4 pathways that the energy can be transferred. So the law of conservation of energy tells us that as an object falls, the gravitational potential energy store is transferred into another store. This is very, very often, not necessarily 100%, but very, very often into kinetic energy. All right, and that's the examples we're going to look at today. So think about a ball. Best yet, grab a ball or something small in your hand that you can toss up for a second. I want you to toss that thing up in the air, whether it be a ball or rubber band, anything, and watch what it does just as it reaches the very top of its height before it starts falling down. So do it a couple times. See if you notice what happens just at that very top when it goes from flying up to coming down. Hopefully you've seen, so that ball, as it falls, so it's going up, and then it comes down. As it falls, it goes faster and faster and faster. It starts here, it's going as fast as it can, it slows down. So we know that kinetic energy has to do with how fast an object is moving. So here it's moving faster. Here all of its energy is in kinetic energy. All right, so it's all in kinetic energy. As it goes up, it slows down. So the kinetic energy on this side, the kinetic energy turns to gravitational potential energy as it goes up. Once it reaches the top here, it is all gravitational potential energy. There's no kinetic energy left. It actually pauses for the briefest of seconds. If you haven't seen that, look again, see if you can notice the pause at the very top. And then it'll start coming down again. So here, it's our gravitational potential energy turns to kinetic energy. And by the time, just before it reaches the bottom, it is all kinetic energy again. Now, when it hits the ground, what does that kinetic energy turn to? In reality, some of it is lost in a little bit of air resistance in heat. Once it hits the ground, it turns very quickly into sound energy, because you can hear it fall and hit the ground. It turns into elastic potential energy, which you notice again if it bounces back up, that's transferred into elastic potential energy, which travels back into kinetic potential energy, and so on and so forth. And some of it turns into thermal energy, from the air resistance. And hopefully you remember air resistance is just friction, the friction force. And we know that friction, it's friction with the air. Friction creates heat. So when you rub your hands together, that friction creates heat. So all energy ends up turning into thermal energy in the universe. All right? That's what they call the thermal heat death of the universe, is that all energy eventually will turn into thermal energy. So the gravitational potential energy that's lost is the kinetic energy that's gained by that ball as it goes up, or as it falls down. So this is just as it comes down. So it has all gravitational potential energy here. As it comes down, it's losing its gravitational potential energy and it turns to kinetic energy. But if it had, let's say, if it had 8 joules of gravitational potential energy here, halfway down, it might have 4 joules of kinetic energy and 4 joules of gravitational potential energy. By the time we get to the bottom, we now have 8 joules left of kinetic energy. Because all of the energy that the ball has here is as much energy as it will have here. It can't have any more. Okay? A tiny amount was lost to the thermal energy with that resistance, or sound energy if it made sounds as it fell. But the majority of it went back into the kinetic energy. Okay, so as it says here, in reality, some gravitational potential energy will be transferred into the thermal store. So how does this apply to questions? How are we going to have questions about this? So if Galileo drops a stone from the Leaning Tower of Pisa, which is 45 meters high. So here we have, you're looking at a question, you're figuring out what it is. We have 45 meters high. This is our height. Right? At what speed does it hit the ground? So we're looking for our velocity. Okay? So it doesn't give us a lot of information here. We don't really know a lot about it. We actually have enough information to answer this question, because we know that it has kinetic energy, and gravitational potential energy. So the first thing we know is that the gravitational potential energy is equal to the kinetic energy. So the gravitational potential energy at the start, so this is the start, is equal to the kinetic energy at the end. So that ties into its speed at the end. And then we write down our formulas of what it is. So gravitational potential energy, we know, is mass times the gravitational field strength times the height. So we start with, so we can plug some things in. We don't know our mass. We know our gravitational field strength is 10. So they've mixed these two around a little bit. So 10 is our gravitational field strength. We know our height, so we can plug that in. 1/2, we know, is 0.5. We don't know our mass, but we know our velocity. Because there's an m here, and there's an m on this side, they actually cancel each other out. Because we can go, if we try to move this m to the other side, we end up with m divided by m. Anything divided by itself is always 1. If you're not sure on that, ask your maths teacher. Otherwise, just trust me. M divided by m is 1, and we're only multiplying, and anything multiplied by 1 is the same. So we can actually just cross those right out. So we end up with 10 times 45 equals 0.5 times speed squared. All of a sudden, there's only one variable left there. Now it's a case of collecting like terms. So velocity squared, or speed squared, is equal to, so we have to take this to the other side and divide it out. So 10 times 45 divided by 0.5, 900, take the square root, because the opposite of square is the square root. So the square root of 900, we have 30 joules. It would not be 30 joules, because what is the scientific unit for speed? Well done if you've written meters per second. All right, so I'll erase this now. I want you to copy it out and add in the annotations and explain to yourself what's happening. So I want you to make sure that you have that all written out into your books. So, what are the energy changes when a ball is thrown upwards? Here's your question. Remember, in science, a well-labeled diagram is worth as much as a full paragraph. So there's a diagram here that you could use to answer that question. So pause the video, answer the question, come back to it. So the energy changes when the ball is thrown upwards. So the kinetic energy, so the ball is given kinetic energy. So I'm going to just draw the arc. 1, 2, 3, 4, 5, and write about what's happening at each of these points. So at 1, the ball is given kinetic energy. 2, kinetic energy turns to gravitational potential energy. At 3, kinetic energy is equal to 0. All energy is gravitational potential energy. And then at 4, the gravitational potential energy is turning into kinetic energy. And at 5, all gravitational potential energy is back to kinetic energy. All right, so that's what we're looking for. If you've written it more as sentences and said, ball starts with only kinetic energy, loses kinetic energy, gains gravitational potential energy as it rises. Once it hits the top, the ball loses all kinetic energy. So I want you to think about, what does that mean if the ball has lost all of its kinetic energy? Yes, if the ball has lost all of its kinetic energy, it has stopped moving. Okay? So the ball stops moving at the top, has lost all kinetic energy. All the energy is gravitational potential energy. As the ball starts falling, the gravitational potential energy turns back into kinetic energy. And when it reaches the same height, all of its gravitational potential energy has gone back into kinetic energy. So if you haven't drawn the diagram, you do have to add more information to your words. All right, because a picture is worth 1,000 words. So here are some more questions. Okay, these go step by step. So looking at here, again, Earth's gravitational field strength, G, is 10 newtons per kilogram. So that's something we know. So that's something we need to write down for every one of these questions. So G is equal to 10. 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 All right, this isn't a G is equal to 10. So we've written that down. So now we look at the next numbers. Diver of a mass 40 kilograms. So we have a mass. Climbs up to a diving platform, 1.25 meters high. So that is our height. What is her weight in newtons? So remember, weight is equal to mass times gravitational field strength. Okay, so they've actually given us the equation, the formula here. So our weight, and I don't like using the W for weight because W actually means work, which we'll learn about later. But weight is equal to mass times G. So we write out our equation again. We plug in our values. We don't know our weight. We know our mass. is 40, and we know our G is 10. So her weight is 400 newtons. So we know her weight. So now, what is her change in gravitational potential energy? So we know, sometimes it's useful to write it down again. We know her mass is 40. We know her height is 1.25. We know G is 10. We know weight is 400. So gravitational potential energy is now what we don't know. We can write down that equation. Gravitational potential energy is equal to mass times gravitational field strength times our height. So our gravitational potential energy is what we don't know. We know her mass is 40. We know G is 10. And we know her height is 1.25. We can plug this straight into a calculator. So 40 times 10 times 1.25 gives us an answer of 500. So our gravitational potential energy is 500 joules. No units, no marks. So at this point, this could easily be worth 6 marks that you have here already. And all you've done is written down what you know, written down your equation, and plugged in your numbers. And plugged them into a calculator. That's all you need to do. Okay? So, have a look at this question, going back to the video to find the rest of the information that you need, pausing the video, giving it a go. We'll come back to it. So, hopefully she walks to the edge of the platform and falls down. This tells us there's no extra energy. Because if she jumped down, she would be putting energy, she would start with kinetic energy, but she's not starting with any kinetic energy. What is his or her kinetic energy as she hits the water? So now we don't know the kinetic energy, but we know from the last question how much gravitational potential energy she has. And we know that she can't have gained any energy, so the gravitational potential energy is equal to kinetic energy. So the kinetic energy is equal to 500 joules. All right, give the next question a try. We have our G. We know our kinetic energy is 500 joules. We know her mass is 40 kilograms. All right, so we have kinetic energy, we have our mass, we want to know the speed is what we don't know. So we write down our equation. So we have kinetic energy is equal to 1/2 times mass times speed squared. So our kinetic energy we have is 500. It's equal to 0.5 times 40 times speed squared. So you'll see now why in all the other lessons I've asked you to write down all the steps. Because now it's easy. You don't have to think about memorizing the other formula because we're using all the different formulas between each other. So once you plug this into 500 divided by 0.5 divided by 40, take the square root. So speed is equal to square root of 500 divided by 0.5 divided by 40. If you need an extra step in between this one and this one, absolutely you are 100% allowed to do that. All right, just for the sake of time, I'm skipping that step, but you can absolutely do that. 500 divided by 0.5 divided by 40. So our speed is 5 meters per second. No units, no marks. So here at this point, this section alone would again be worth 4 marks. We'd have 1 mark for the equation, 1 mark for plugging in the values correctly, 1 mark for arranging the formula, and 1 mark for the correct answer plus the units. All right, so another diver, mass 80 kilograms, climbs to the 5-meter platform. What is her speed as she hits the water? So this one, we have to do some extra steps. So it's essentially tying all the other questions into one. So pause the video, give it a go, look back and re-watch the other parts if you need to remind yourself. The answer will pop up in a minute. So here's the worked out full-on answer. So I've written down here the things that we know from the question. So we know the mass and we know the height. We don't know the speed. But with the mass and the height and the gravitational field strength, I can figure out the gravitational potential energy, which I know is tied to kinetic energy, so that's a good place for me to start. So I know my gravitational potential energy is 400 joules. So I know as she falls, all of her gravitational potential energy turns into kinetic energy. So I know those 400 joules is the same as her kinetic energy. So I can plug that now into my kinetic energy formula, and I can end up with a speed of 10 meters per second. Remember, no units, no marks. So hopefully you've noticed that the speed from the one answer to the other has doubled. Okay? The mass has doubled, the height has changed, but the speed has only doubled. So, looking at question 7, giving it a go on your own, emailing your teacher with the answer if you get it. So, Galileo, famous old scientist from a long, long time ago. Before Galileo came Aristotle, and his scientific theory was that heavier objects fall faster than lighter objects. If I came up to you and mentioned this to you, you'd say, yeah, no, that makes sense. Most people believe that heavier objects fall faster. If you take two objects that are the exact same size, but different masses, and drop them at the same time, they will actually fall at the same speed. So Galileo showed that two balls of different weights will hit the ground at the same time if they have the same size and the same air resistance. Okay? Thus disproving Aristotle's theory. And this is, as we know, how science continues to go on. One person has a theory, the theory is disproven with new information, with a new experiment that comes out, and science goes on and on like that. So, because the mass is cancelled, it is not a factor in the ball speed. It doesn't matter how big the mass is for it to affect the ball speed. What is the issue is that air resistance. All right? The same way, you can have two things of the exact same mass. I want you to take an old spare piece of paper that's uncrumpled and drop it, and notice how long it takes to fall. Then I want you to take that exact same piece of paper, hold it up to the exact same height, but crumple it into a ball this time, and then let it fall. It falls so much faster in the shape of a ball because it has far less air resistance. Okay? So if they're being dropped from the same point, the gravitational field strength is the same for both balls, and so they fall at the same rate. So that's something you just need to know. The mass doesn't actually matter how much it falls or how quickly it falls. What matters is how high it's come from and how high it's come from. So, looking now at this final knowledge check, giving these questions a go, and coming back for the answers. And here are the correct answers for those questions. Any questions about those, make sure to email your teacher. Don't forget to do any follow-up activity that your teacher has set, whether that be some kind of quiz on EduCake or anywhere else or anything else. And until next time.